Hello dear students. So in this video, we will be discussing gravitation PYQ from April 2024 attempt. Before this, we have also discussed PYQs of Kinematics, NLM work energy, ray optics and electrostatics PYQ of 2024. You can go and check the link in the description box. So let us start with this. Yeah. So the question we have, it says a 90 kg body placed at 2r distance from surface of Earth experiences gravitational pull off. Fine. So let's draw the situation. This is, let's R at a height of 2r, a 90 kg body is kept. They are asking us the gravitational pull. How to do this? What do we write? Gravitational pull in terms of masses we can write as m into g. Now g over here, as we know that g varies. G varies with height, g varies with depth. So if it is on the surface, g value will be 9.81 or 10. And if we take it to a height of h, your g value will vary. So over there, let's say that at a height of 2r, g is g dash. Let us calculate this. So g dash will be g times r by r plus h whole square. This is your variation of g with height, right? This is what is our relation. So g dash is equals to g times r by r plus h. How much is the height given from surface? 2r. So 2r whole square. Let's simplify this. G into this will be r by 3r. R will cancel. We'll have 1 by 3 whole square. So ultimately we get g dash is equals to g by 9. So if we write down the force, it will come out to be mg dash, which is equals to mg by 9. Let's substitute values over here. M is your 90 kg. G is 10 by 9. So this gives us 100 Newton. So our gravitational pull at a height of 2r is 100 Newton. You can check the options are there for you. All right. Let's move ahead. Yeah. So the question that we have, it says, correct formula for height of a satellite from Earth's surface is. Now 4 options are given to us. If you check, the height is asked in terms of T, capital R, small g and capital R. T is time period, R is radius of Earth, small g is acceleration due to gravity. So we need to find out height of satellite in terms of TRG. Let us calculate. So let's say this is our Earth having radius R, a satellite revolving around in a orbital radius of small r and at a height of h. Let's say at a height of h. Right. This is our satellite. So this is what is given to us, right? What is our time period? What is our standard result? Time period is given as 2 pi by root gm small r power 3 by 2. Small r power 3 by 2. Over here, small r is the orbital radius, which is nothing but your capital R plus h. H is the height from the surface. So what can I write it? Over here, this can be written as, if we square it, if we square both the sides, we will get t square is equals to 4 pi square by gm. And this thing, in place of small r, I am putting your capital R plus h. So this will become capital R plus h whole cube. Right? Let's simplify this. We want h value. So over here, I can write as gmt square by 4 pi square is equals to r plus h whole cube, right? Now over here, beta, if you notice, the answer is given in terms of small g. We have this capital G, your gravitational constant. Let us change it. What can we write it? Small g is equals to capital G m by r square. So over here, I can write it. Let's take r square and r square. And this gm by r square will become small g. Therefore, I can write it small g t square capital R square by 4 pi square is equals to r plus h whole cube. Let us take cube root on both sides. So we will get G T square R square by 4 pi square whole power 1 by 3 is equals to R plus H. I think you got the answer. You can check the options, right? Let's check the option, which one it will be. H value will be minus R will come on the LHS side. Which option we are having? T square R square G by 4 pi square whole power 1 by 3 minus R. This will be option number 2. And options are there for you people. So option number 2 will be our correct answer. Let's move ahead. Yeah. So the question that we have, it says a simple pendulum doing small oscillations at a place R height from Earth's surface has time period T1 is equals to 4 seconds. T2 would be its time period if it is brought to a point which is at a height 2r from Earth's surface. Choose the correct relation between T1 and T2. Right? Question is there for you. Now, let us see. So what we have is at a height of r. Over here, the time period of pendulum is given to us T1, which is 4 seconds. And when it is taken to a height of 2r, the time period becomes T2. What is the general result of time period of pendulum? Time period of pendulum is given as 2 pi root over L by G. Why will time period change? As we move it from R to 2R, basically G value will change, right? Variation of G with height. So when G value will change, time period also changes. So let us calculate G at a height of R and G at a height of 2R. Over here, let's say that this is G1 and this is your G2. So what can I write it? Let's write down G1 is G times R by R plus H. How much is our H? H is equals to radius of Earth only, which is given as R whole square. So G1 is equals to, this will be R by 2R. 2R, it will be 1 by 2 square. That will become G by 4. G1 comes out to be G by 4. G2, if I calculate, G times R by R plus H. H over here in the second case, it is 2R. So R plus 2R whole square. This value will come out to be G by 9. Equation 2, right? Now, let us calculate T1 and T2. T1 will be 2 pi root over L by G1. G1 is G by 4. So, this thing comes out. T1 is equals to 2 pi root over L by G into 2. And T2 is 2 pi root over L by G2. G2 is how much? G by 9. I'll substitute over here. G by 9. So, this thing comes out 2 pi root over L by G into 3 times. T1 can be written as, is it visible to you there? No, 1 minute. So T1 can be written as, sorry, is it visible? Visible is it. T1 is 2 times T and T2 is 3 times T, right? T is basically time period on the surface of Earth that we have already written. So let's take the ratio. What do we get it? T1 by T2 will be equals to 2 by 3. From this we can write down 3 T1 is equals to 2 T2. Check the option. This will be your answer. Let's move ahead. Yeah. So the question we have, in hydrogen-like system, the ratio of Coulombian force and gravitational force between an electron and a proton is in the order of. Fine. So how to do it? Hydrogen-like system, basically 1 electron and 1 proton. 1 electron and 1 proton. This is what they are talking about. Ratio of Coulombian force by gravitational force. So force Coulombian by force gravitational. What is our Coulombian force? For this pair, if I have to write down Coulombian force, electric force, it will be K Q1 Q2 by R square. Gravitational force will be G M1 M2 by R square. Ultimately, we get K Q1 Q2. Now, for electron and proton, the magnitude of charge is same only. So, therefore, we can write KQ square by G, mass of electron, mass of proton. Let's put the values over here. K is 9 into 10 power 9. Q, 1.6 into 10 power minus 19 whole square divided by G, 6.67 into 10 power minus 11. Mass of electron, which is 9.1 into 10 power minus 31. Mass of proton, which is 1.67 into 10 power minus 27. Right, kg. So over here, if we write it 9 into 1.6 whole square, 10 power 9 into 10 power minus 38. In denominator, we can write down 6.67 into 9.1 into 1.6 into, this will be 10 power minus 42 into 10 power minus 27, right? This is what we are getting. When we further simplify this, our result, basically you don't need to calculate it to the exact value. They are just asking us, it is in the order of. So when you will simplify these, you will find out that this comes out 10 power 39. And this will come out to be 10 power 39. Fine. Let us move ahead. Yes. So next we have a match the column. The question is there in front of you, right? Different physical quantities they have given. They have given mass of sun as ms, mass of earth as me, radius of earth as r, and distance between sun and earth as a, right? Kinetic energy of earth. These are all standard result. We know kinetic energy. Kinetic energy is written as basically G me ms by 2a, right? This is your kinetic energy for two mass system. This is what is the kinetic energy that we get. Second option that they have, this they are saying potential energy of earth and sun. Potential energy for two mass system, what it is? Minus G m1 m2 by r. This I can write as G me ms by a. A is the separation. Next is your total energy. Sorry. C is total energy of the earth and sun. Total energy, if you like, you do the summation of it, or we know it is minus G me ms by 2a, right? Fourth part. What is our fourth part? Fourth part says escape energy from surface of earth per unit mass. Now escape energy from surface of earth. What is our escape velocity? Velocity escape is root over 2gm. Now this m is the capital M, mass of earth, not mass of the particle. Capital M by r. Root over 2gm by r is our escape velocity. So if you want to find out the energy which needs to be given, it is your, this is the energy that should be given. So half mve square. If we do it over here, 1 by 2 mve square. If we do it, 2gm by r. Ultimately, we get over here G capital M small m by r. But in the fourth part, as you can see, they've asked us escape energy from surface of earth per unit mass. So for per unit mass, we can write it as G capital M by r, right? G capital M by r. I hope this is okay to you. And now you can match all the options now. Let's move ahead. This was the options. And these were the options. You can check it and you can match according to our answer that we have got. Let's move ahead. Yeah, the next question that we have. A satellite revolving around a planet in stationary orbit has time period of 6 hours. So time period of satellite around a planet is 6 hours. That's why I'm written TP, time period of satellite around a planet. Fine. Of a stationary orbit. Fine. The mass of planet is 1/4 of the mass of Earth. MP is given to us ME by 4. Well and good. The radius of orbit of planet is, they are asking us RP. Okay. It is given to a stationary orbit. That means we have to consider the radius of the planet itself or radius of Earth. And in the question, they have given us radius of geostationary orbit for Earth is 4.2 into 10 power 4 kilometer. So radius for Earth is given to us as 4.2 into 10 power 4 kilometer. How to solve it? See over here. Time period. Time period for a satellite. What do we write? T is equals to 2 pi by root gm r power 3 by 2. And over here, it is stationary orbit, so capital R power 3 by 2. We can simplify this. T square will be 4 pi square by gm r cube, right? Over here, if you notice, we can get the proportionality. T square is proportional to r cube by m. This is what we are getting. Now, we have to compare for your planet and for your Earth. For Earth, how much will be the time period? For Earth, the time period is 24 hours. This will be the time period for a stationary orbit satellite. Now, so we can write time period of planet square by time period of Earth square is equals to Rp by Re whole cube into Me by MP. Fine. Let's see over here. So, Tp by time period, we can write it 6 by 24 square is equals to Rp. We have to calculate this by Re, which is given to us, into Me. Me by MP is Me by 4. So, ultimately this comes out to be 1 by 4. 1 by 4 square will be 1 by 16. And from there we get one more. 4 is equals to Rp by Re whole cube. So, further if we simplify it, I am taking it over here. Rp by Re whole cube is equals to 1 by 64. So, Rp is equals to 1 by 4 into Re. We'll take cube root on both sides. So, ultimately, Rp is equals to Re is given to us. This is what we have to take. 4.2 into 10 power 4 by 4. Simplify it. Check the option. If we check the option, the 4 options that we have, we'll be getting over here option number D, 1.05 into 10 power 4. 1.05 into 10 power 4 kilometer. This will be our answer, right? It's there for you people, option number 4. Let's move ahead. Yeah, our next question, it says, to project a body of mass small m from Earth's surface to infinity, the required kinetic energy is, answer is given in terms of small g. How to do it? See over here carefully. Required kinetic energy, they are asking us. Do we know the required velocity? Yes, that is your escape velocity. Velocity escape is root over 2gm by r. Kinetic energy, if we calculate, it will be 1 by 2 mve square. So, 1 by 2 mve square to capital G m by r. Cancels out. G capital M small m by r. Now, beta, this capital G m by r, what can we write it? Capital G m by r can be written as small g into r. And if you know this, well and good. If you don't know it, keep this in mind. Many a times this small g is used. We use this capital G m by r as small g or gm as gr square, whatever according to the situation. So, therefore, we can write it small m g r. And r is the radius of Earth. You can check the options. I'll check it for you. mgre. They given in terms re. Re is taken as the radius of Earth. Fine. So, mg re. Option number 2 will be our correct answer. Let's move ahead. Yeah, the question that we have, it says, assuming the Earth to be a sphere of uniform mass density, a body weighted 300 Newton on the surface of Earth, how much it would weigh at r by 4 depth under the surface of Earth? Fine. So, Earth, yeah. Over here, the weight is coming as 300 Newton. They are asking us at a depth of r by 4. What will be its weight? D is equals to r by 4. Why weight will change? Because g value will change. What is the variation with depth? Variation of with depth for g is gd is equals to g times 1 minus d by r. Right? Let's simplify this. So, gd is equals to g times, please remember this. I hope you know the result. If you don't know it, you have to check it also. We have made a revision video for gravitation chapter also. It's all the relations are covered, all the relations concepts are covered for gravitation chapter. You can check the link in the description. Now, coming back to our question, GD is equals to G times 1 minus D. D value is given to us R by 4 into R. Cancels out. Ultimately, we get GD is equals to 3G by 4. Now, so weight at a depth of D can be written as mgd, which is basically m into 3g by 4. 3 by 4 mg, and mg is on the surface, which is given to us 300 Newton. So 3 by 4 into 300, it comes out to be 225 Newton as our answer. Let's move ahead. Yeah, so the question that we have, it says two planets A and B having mass m1 and m2 move around the sun in circular orbits. And it's given to us in circular orbits of r1 and r2 radii respectively. If angular momentum of A is L and that of B is 3L, the ratio of time period TA by TB is fine. Now, it should be a simple question. So, TA by TB, they are asking us TA by TB. Some information is given to us, R1, R2, M1, M2 and angular momentums are given. So beta, what is the relation time period for in a circular orbit? We know time period is proportional to R power 3 by 2. So T square is proportional to R cubed, right? This is what we have. So ideally, if we have to write TA by TB, it should come this. From this relation, we can write down TA by TB is equals to R1 by R2 whole power 3 by 2, right? This will be our answer. But if you check all the options that are given, option is not there. R1 by R2 whole power 3 by 2 is not there, right? So R1 by R2 whole power 3 by 2 is not there. It is there in terms of R1, R2, but not this. And answer is given in terms of masses also. So how to do it now? See over here, it is given to us that angular momentum is given to us. So for first, angular momentum is given L. Angular momentum can be written as m1 v1 r1. Angular momentum for the second planet we can write as 3L is given, which can be written as m2 v2 r2. 3L is given, 3L, yes, 3L is given, which can be written as m2 v2 r2, right? First, second. Let's take the ratio over here. If we take the ratio, 1 by 3 is equals to m1 v1 r1 by m2 v2 r2. Now, what do we know about v1 and v2? v1 and v2 are basically your orbital speeds. And for orbital speeds, I know v is equals to root over gm by r, right? Root over gm by r. This is what is your orbital speed. So from this we get v is proportional to root over 1 by root over r. From here, from this we can write down v1 and v2 value. 1 by 3 is equals to m1. v1 by v2 can be written as root over r2 by r1. So root over r2 by r1 into r1 by r2, and you have m2. This cancels out. We get over here 1 by 3 is equals to m1 by m2 into root over r1 by r2. Now see this. This is what we have got it. Root over r1 by r2 value. Let's bring it over here. Let's substitute over here. So TA by TB is equals to r1 by r2 root. r1 by r2 root can be written as m2 by 3m1 whole power 3. Please check it. I hope this step is clear. I have substituted over here r1 by r2. Root over r1 by r2 I have substituted as m2 by 3m1. So what do we get it? TA by TB is equals to 1 by 3 cube. That will be 1 by 27 into m2 by m1. This will be our answer. In terms of masses, this will be our answer. You can check the options. Options are there for you. Option is option number 3. Option number 3 will be correct answer. Yeah, so the question is, two satellites A and B go around a planet in circular orbits having radii 4r and r respectively. So for A, the radii is 4r, or B, radii is r. Okay, if the speed of A is 3v, speed is for A is 3v, what is the speed of B? Right? Let's solve it. Simple question. Orbital speed. Orbital speed is given as basically root over G capital M by R. Root over G capital M by R. So from this, what can we write? VA will come out to be root over GM by RA, which is your 4R, and VB will be root over GM by orbital speed for B is R. Let's take the ratio. This is 1. This is your 2. If we take the ratio, VA by VB is equals to root over R by 4R. That is, VA value is given to us 3V. 3V by VB is equals to 1 by 2. That implies VB value comes out to be 6V. Right? Let's move ahead. Yes. So let us take the look at the question. The question says, an astronaut takes a ball of mass small m from Earth to space. He throws the ball in a circular orbit about Earth at an altitude of 318.5 kilometer. Altitude is given. That means h is 318.5 kilometer given. So at a height of 318.5 kilometer, the mass will be moving around in the orbit, है ना? Basically circular orbit around Earth. Fine. From Earth's surface to the orbit, the change in total mechanical energy of the ball is given as x GME by 21 RE. So this is what is the change in total energy is given to us, x GME by 21 RE. Fine. When it is taken from Earth's surface to that orbit, and then in orbit when it is moving. Fine. The value of x is, take RE as 6370 kilometer. Fine. See over here. 6370 kilometer. First of all, change is what? What is change in energy? Change in total energy will be the total energy final minus total energy initial. Initial total energy. Total energy initial. Initially, when it is on the surface it will have only potential energy. What is your gravitational potential energy? Minus GMEM by R. Gravitational potential energy minus GMEM by R. Okay. First, total energy final. Total energy final. Final total energy will be your summation of kinetic energy plus potential energy, and that is given as minus GMEM by 2R. This is your 2 small r, that is your orbital radius. Please be careful, on the surface only potential energy is there. Therefore, I have written minus GMM by R. Whereas on the orbit, in the orbit, it is moving around in the circular orbit. So it will have kinetic energy and potential energy. And the total energy, when kinetic energy and potential energy is there, is minus GMEM by 2 small r. Small r is the orbital radius. How to calculate orbital radius? They have given us h value. So orbital radius r will be capital R plus h. From this, let us do the calculation. H value, beta, if we see, this is radius of Earth given to us. I'm doing it over here. So what can I write it? H by RE is equals to 318.5 by 6370 kilometer. When you will solve it, you will get it 20 times, right? So from this, what can we write it? H is equals to R by 20, RE by 20 or R by 20. So this height is 1 by 20 times the radius of Earth. Let's substitute over here. So small r comes out to be R plus H. H is capital R by 20, which we will get it 21 R by 20. I hope it's visible over here. Fine. This is, I'll substitute, minus GMEM by 2 times of 21 R by 20. We get over here 10 times. So minus minus 10 GMEM by 21 R. This is our total energy final in the orbit coming. Second, let's do it final minus initial, which can be written as minus 10 GMEM. It's visible there. I'll do this side. So change we have to write basically. Yeah, change we can write it as T final minus T initial, which will be minus 10 GMEM by 21 R, minus of minus plus. This is our initial energy plus GMEM by R. Okay, fine. Let us simplify this. What can I write it over here? 21, 21. So this becomes your 11 GMEM by 21 R. This is our answer. This is the change in total energy. Now you can compare it. X is equals to what? 11. So X is equals to 11. This will be our answer. Let's move ahead. Yeah. So the question we have, it says, a satellite of 10 power 3 kg mass is revolving in a circular orbit of radius 2r. Fine. Mass of satellite is given to us as 10 power 3 kg. And the orbital radius is given to us as 2 times capital R. Fine. If 10 power 4 R by 6, I hope it's little, the font may be little small. So what they have given is 10 power 4 R by 6 joule. This is what is given. If 10 power 4 R by 6 joule energy is supplied to the satellite, it would revolve in a new circular orbit of radius 2.5 R, 3 R, 4 R, 6 R. Options are given. Small g is given 10 and capital R is the radius of Earth. See, let's see. Initially, it is already moving in an orbital radius of 2R. It will have some energy. What is the total energy of a satellite? Total energy of satellite is given as minus GMEM by 2 times small r. Small r is the orbital radius. Right? Now over here in the question, because small g is given to us, let us convert this relation in terms of small g. What can I write it, beta? GME, we know GME by r square is basically your small g. So from this, GME can be written as small g into r square. So therefore I can write it minus small m, that is mass of the satellite, into G capital R square by 2R. This is our total energy in terms of small g and mass of satellite. Keep this in mind. It will be helpful to us. Fine. Now let us calculate our initial energy. Initial energy, total energy initial will be basically minus m, 10 power 3, g is 10, r square divided by 2r over here. This will be 2 into small r. This will be 2 into small r. That is orbital radius. So 2 times of 2r. Initially it is having orbital radius of 2r. Fine. What are we getting? Minus 10 power 4r square by 4r. Cancels out. Minus 10 power 4r by 4. This is our total energy initially. Now this much amount of energy is added to it. Let's see. So total energy final will be minus 10 power 4r by 4 plus 10 power 4r by 6. Let us simplify this. This will become over here. Right? We are getting over here minus times 10 power 4r by 12. This is our final total energy, right? Whatever, in whichever orbit it will go once energy is given to it. So let us compare it with our initial result that we got in terms of small g. So we can write minus 10 power 4r by 12 is equals to mg. M is your 10 power 3. We'll substitute directly. So we get over here 10 power 4 r square by 2 times into small r. 2 times into small r, the new orbital radius. New orbital radius. Fine. 10 power 4 r, 10 power 4 r cancels out. We have 6 times. This minus will also cancel. We have small r is equals to 6 times capital R. small r is equals to 6 times of capital R is our answer. I hope this is okay. Let's move to the next question. So with this, we have almost done. Last question is there. Let's look at it. Yeah. So the question that we have, it says a metal wire of uniform mass density having length capital L and mass capital M is bent to form a semicircular arc, and a particle of mass small m is placed at the center of the arc. The gravitational force on the particle by the wire is fine. Let us draw the situation. So a wire is there, mass is capital M, length is L. This is turned into a semicircular arc. Let's say that the radius of the arc is capital R. And for our understanding, we are taking it. And over here at the center, a small mass M is kept over here. They are asking us the gravitational force on this. What will be gravitational force? Gravitational force on this will be M into G, the gravitational field produced by this semicircular arc. If you know the result of G due to semicircular arc, you directly substitute and you will get the answer. If you don't know, you will have to derive it. Let us derive that result I am doing over here. So let's say, due to this semicircular arc, if we have to find out gravitational field, what I do is, at an angle of theta, I take a small element which subtends an angle of d theta, right? So at an angle theta, I am taking a small element which is subtending an angle of d theta at the center. Due to this small element, what will be the gravitational field direction? Gravitational field direction will be basically over here, it will come towards the mass, and which we will write as dg. dg will be g dm by r square. What is our dm? dm is the mass of this small element. How much it will be? dm will be m by length, which is capital L, m by L into the length of the small element. Length of small element will be r into d theta. Okay, fine. Over here, beta, we can also see r value, capital R we have assumed. They have given to us as length L. Over here, we can write L will be equals to what? The length of semicircular arc, which is your pi into r. So r value comes out to be L by pi. I'll substitute over here. So dm is equals to m by L into r can be written as L by pi into d theta. L cancels out. We have m by pi into d theta. This is our dm. Now, one more thing that you need to understand over here is that this dg that we are having, this dg will have two components. One will be horizontal component, which is dg sine theta, dg cos theta, and then there will be another vertical component which will be dg sine theta. If you notice carefully, for all the small elements that you consider, only dg sine theta will come. dg cos theta component which are horizontal. For this one over here, dg cos theta is coming over here. For this element over here, just at the opposite end, the dg cos theta component will come over here. That means they will cancel each other. So dg cos theta component cancels. Only sine theta component are there. So we need to add, or we need to integrate only the sine theta component. So finally, G will be integral dg sine theta. From where to where? Limit will be coming. Theta I have assumed over here. So for full ring, it will be 0 to pi. 0 to pi. So G is equals to integral dg. dg, if we write it, it will be g dm. dm is m by pi d theta. M by pi d theta into r square into sine theta. R square will come out to be your L square by pi square. So let us substitute integral gm by pi L square into pi square, and we have sine theta d theta. Fine, pi cancels out. Let's take all the constants outside. gm pi by L square integral of 0 to pi sine theta d theta. Integration sine theta d theta, when we'll do it, it will come out to minus cos theta. Limit from 0 to pi. Ultimately, you will get for this one answer as 2. So our small g value comes out 2 times G capital M pi by L square. Once we have got our small g, your force will be, force we can write small m into g, that is 2 times G capital M small m pi by L square. Right? This is our answer. So